So hello everyone, my name's Tom Hayes from the University of Warwick, previously at Durham when I did my PhD and postdoc. So Joss asked me to give this talk on resonant X-ray reflectivity, and I'd like to thank him for that opportunity and to thank him for enabling me to waste my weekend cobbling something together on one of the nicest weekends in England for a long time. So this is a very personal and somewhat introspective look at resonant X-ray reflectometry, and is primarily I was asked to look at it from a didactic perspective with a couple of examples towards the end. So the seminar is sort of split into two. So we'll talk about what resonant reflectivity is, and I apologize for the majority of you who know this probably better than I do, but hopefully you won't get too bored with the pretty pictures. And then a little bit at the end on some sort of aspects of what I've been doing using that technique in the more recent past. So of course we can't do any of these things without a vast list of helpers and collaborators. So too many to list, I'm afraid, for a lot of things. A lot of the samples came from recent collaborations with Durham through the group of Dell Atkinson and in Uppsala through the materials physics group under Björkvin Hortvarsson. Our funding comes primarily from EPSRC, and any of the fits that you see will have been done through GenX, which I'm sure many of you are aware of. So to do resonance scattering, resonance really means about moving and changing energies. So we have to go to synchrotron sources. So some of the data comes from Argonne, some from Brookhaven, and a little tiny bit from the Xmas beamline at DSRF. And we also dabble with some neutrons occasionally, and all of those have been taken at ISIS. So I thought I would start a little bit, not with resonance, but looking just at X-ray reflectometry and the health warnings that come with it. So, you know, we're quite used to looking at reflectivity. We're all reflectivity experts, of course. So, you know, here is just a simple example of something we've been playing with on strontium titanate, lead titanate multilayers. And, you know, when you sort of like try and sell reflectivity, you sort of sell it on the basis that it's a really great technique for looking at things like the number of layers that you can measure, what the repetition is, the layer thickness, interface widths, and all these sort of things. And we sort of try and couch our fitting and our understanding of samples in reflectivity from almost a biased input data, where we think of our sample in real space and we think of how our systems are all lined up in these thin layers, and we think of our sample in the real space geometry, and we map that into what we measure in reflectivity. But of course, actually what we fit in the reflectivity program is not the layered structures. We actually are trying to find an SLD which represents the data, and then we infer from our fitted SLD what the layer structure is. And because we tend to have this biased model in our minds about what the sample looks like, quite often that goes through into how the models are inputted into the computing programs that generate the SLDs. We think about our results coming from the layered structure as opposed to what we really measure, which is the SLD. Now, of course, in the SLD, one of the real problems are how we couple everything together. So, you know, these shaded areas are the PTO lead titanate layers, and you can see as a function of the lead titanate thickness, the density of this layer is apparently changing. That is actually a real phenomena, but in many reflectivity analyses, we sort of like lose sight of the fact that within a single X-ray energy, we don't really have the ability to separate out density from composition, even though density and composition are separate inputs into our model. So within that framework, we have to be a little bit careful. And most packages set up the reflectivity in this sort of way, in that each layer is defined by its refractive index, and that refractive index is defined variously, but essentially there's a density term. So this is the number of scatterers, and this is the scattering strength. So this is the scattering factor. So this is the composition side, and this is the physical density side. And of course, those two are multiplied together. So you can never really separate those from a single measurement. And if separating out the density and the composition is important, then actually you can't do that from a single X-ray or neutron reflectivity curve. So one thing that a lot of people do, of course, is to combine multiple techniques. So in this case, we have a cobalt iron aluminium silicon Heusler alloy on silicon, and we were trying to measure the composition and the structure of it from both a magnetic perspective and also from a structural perspective. And you can see that on this left panel here, we've got various different models to fit the data, and actually the SLDs that those different models have are quite different. And actually, you wouldn't necessarily be able to tell anything about the models, the robustness of those fits, simply from the quality of the data fits, which aren't too bad, and both are pretty similar. So even when you've got good fits to the data, there is this sort of somewhat health warning issue on how you can go about trying to separate these models. In this case, we explored the sample with some high resolution microscopy. So we used eels and we used HADSTEM to try and also focus in on what the compositions actually were. But of course, with the microscopy image, you're actually looking at quite a myopic region of the sample, and in the reflectivity, you're looking at a much larger average. So it's not quite as straightforward as taking the elemental profiles and then turning them into scattering length densities and then trying to refit the data. That didn't work quite either. So there are problems inherent within the technique of trying to find robust fits, certainly if you're trying to focus on composition and density. And one way around it is to try and change the contrast of our layers somehow so that we can get more information from the same sample. So the neutron and X-rays have very different scattering length densities for the different elements. That's one contrast mechanism, but in neutrons, of course, you're limited in the Q range that you can probe because of the flux. So can we, within an X-ray environment, also develop contrast mechanisms? And those contrast mechanisms come about from the resonant X-ray scattering. So resonant X-ray scattering can be also referred to as anomalous dispersion. So if you think of what an X-ray does when it interacts with an atom, that X-ray couples with the electrons inside the material, and we quite often think of the scattering factor as simply being the number of electrons. So in the freestanding ideal case, the scattering factor is just the number of electrons. But of course, in an atom, those electrons are not free. They're bound by some absorption by the Coulomb interaction here. So you can think of this as being a bit like a driven oscillator with some sort of spring constant, depending on how those electrons couple to the nucleus. And that coupling here introduces these two additional terms, which are purely energy dependent. And these are the anomalous dispersion terms, and are related to how the scattering contrast changes as you approach a resonance in the system, i.e. as you approach the absorption edge, where this coupling factor becomes strong. And in terms of what that does to the scattering factors, are shown here on the right. So there are two, there's a real and imaginary part, as there must be. So our refractive index here has got these anomalous dispersion terms in, and as an example here for iron, up around 10 keV, where we expect it to be, it's around Z, so this is 26 for iron. But if you tune close to an absorption edge, what happens is these real and imaginary anomalous terms kick in, and essentially what happens is you get large changes in the scattering factor close to those absorption edges. And you can see this is the real part, has a large dip in it, and these are the absorption jumps at the same energies, of course. So where the absorption increases at the K edge, you get a dip in the real part of the dispersion correction. So what that effectively means is that if you tune to some of these edges, then close to that absorption as the refractive index of that particular element is going to change. So if you've got a layer which has got some iron in it, then the iron layer is going to have a different refractive index as you tune on and off the absorption edge. And of course, that means that the density doesn't change, but we can change the scattering factors simply by changing the energy. So in this example of an iron chromium multilayer, which has just been simulated, you can see that the Bragg peak intensity is going to be proportional to the difference in the scattering factor contrast between, sorry, that should be chromium and iron. And as we tune on to the iron edge, this Bragg peak intensity increases dramatically because of this dip in the absorption edge. And we can use this phenomena to perform reflectivity curves at different energies, and that's one way of introducing a new contrast mechanism. But once upon a time, we also focused by sitting on this Bragg peak and scanning the energy. So this was a permalloy copper multilayer, and this is the experimental data. So this is the fixed Q scan as you go through the iron, the nickel, and the copper edges. And if you just assume a simple bilayer material with standard densities, then you'll find that you can't get the data to fit over the whole of the energy range. And actually what we found was that introducing a small strained interface layer of a slightly different density, but of the same composition, actually changes quite a lot the real part of the scattering factor contrast and changes how the intensity of the Bragg peak changes as a function of energy. So to fit the energy dependent data, you have to introduce this strained layer into the permalloy layer itself. And it's this ability to focus in on density, which really is quite a powerful technique if you can follow this energy dependent scattering. One of the other advantages, of course, is if you do an energy scan at fixed Q, you will also, within the scattering contrast, pick up the x-axis fringes, and by subtracting the atomic contribution, you can also get the radial distribution functions from these oscillations. And you can see that the experiment here was looking at how that changed with temperature, and as a function of temperature, the copper didn't change, but the permalloy had some changes as we annealed the sample. So this is one way of using resonance to explore how you can separate out composition and density, but not all absorption edges are equal. So I'm sure many of you are aware of the XMCD phenomena. So certain absorption edges, and particularly those in which you've got a direct dipole transition from a spin split, from a core state that's split into the Fermi level, which is spin split, then if you come in with left or right circularly polarized light, you preferentially pick up a spin up or a spin down electron from in here. And of course, the spin split D state gives you a spin filter. So the transition probabilities of left and right circularly polarized light are necessarily different. So, and they also depend on the magnetization, which defines this D state in here. So what the XMCD is very powerful at doing is using that absorption contrast to give you differences at the L3 and the L2 edges, from which you can extract the spin and the orbital contribution of the magnetization. And that's the basis of the XMCD sum rules. And what we did many years ago was to recognize that if this is the absorption part of it, then you also, by definition, through the Kramers-Kronig transformations, must have a real part as well. So essentially, our scattering amplitude on some of these magnetic-y type resonances are the original anomalous dispersion terms that we had before, so E and Q, but it also must depend on the magnetization M. And we can formulate this in different variant ways, but one of the more standard ways to do it is to reformulate it into a 2x2 matrix, which is looking at the polarization dependence and how that polarization dependence couples to the magnetization. So we can consider our X-ray beam to be pi and sigma polarized. We take a circular polarization, which is just a linear sum of the two, and we propagate it through this 2x2 matrix. And essentially this first term here, which is the dot product of the two polarizations, this F0 term here, that's the original anomalous dispersion terms. And then there's a second anomalous term here, this F1 term, in which the cross products, instead of the dot product, couple into the magnetization direction itself. So we can assume that we've got some in-plane polarization, and we can simplify this 2x2 matrix. And essentially what comes out is that we have the scattering cross-section now that's just dependent on the in-plane components. We have a resonant term here, which is just due to the chemical structure, and one due to the magnetization. And then if you were to reverse the magnetization or change the helicity and take the difference, then of course what you end up is you cancel this term and you end up with a term that is just proportional to the magnetization in the sample. So reformulating this in how we had our reflectivity model before, there's nothing changed about how the modeling goes, how the input goes. We still are defining our layers through refractive indices, but now our real and our imaginary parts have an additional term. So you can think of this now as the magnetic analog to the charge dispersion term. So this is magnetic dispersion and this is magnetic absorption. So this is the XMCD and this is the cross section coming from the real part of that. And then we extract the magnetic information by taking the flipping ratio of the two data sets. So some early examples, going back to the time of Daresbury, this is just a simple nickel film recorded under two magnetization directions, and you can see that there's a slight difference in the reflectivity curve. And of course, if you then just scan the field, you get nice hysteresis loops. On this example of antiferromagnetically coupled copper cobalt multilayer, if you tune to the cobalt edge, you clearly see a second order, a half order antiferromagnetic peak, which doesn't exist on the copper edge because this is, if you remember, an element specific resonant technique. So this is a really great place to start and opens up the possibility of measuring magnetization and magnetic properties of materials. But the problem comes in that these optical components, this F0 and F1, are generally not so well known because essentially we're not dealing with the K states, we're dealing with L and in some cases M edges, where the screening effects become quite important. And actually the quantum computing, the quantum Hartree-Fock calculations that try to calculate these terms generally have very large uncertainties and are generally wrong. And of course, they are also modified by the local chemical environment. So as a practitioner, we have effectively two possible approaches. One of which there are many good examples in the literature is where you do the full analysis. So you do the reflectivity, you also look at the XAS and the XMCD, and from that you experimentally determine these scattering factors to give you a complete picture of the sample. Or you do what I do, which is generally break that possibility of doing pure magnetic scattering, and we fix the magnetic moment, and we then allow the real and imaginary terms, we fit this. And what that gives us is the possibility of measuring magnetic profiles. It gives us the possibility of measuring magnetization loops. But what it doesn't enable us to do is to give us absolute values of the magnetic moment. And my job over the next 5 minutes or so is just to flash through some of the examples we've been doing and highlight what is possible at the moment using this approach. So here is one example which is based on the iron-palladium system. So iron-palladium, if you remember, is very close to being a ferromagnet. It doesn't require a lot of transition metal to make it magnetic. It's very susceptible to magnetic to have a magnetic moment induced on it. So we looked at how that iron could be distributed within palladium. So this is just a single thin film of a palladium iron alloy, and it's represented here. By distributing the iron atoms throughout that palladium layer, you end up with a slab of uniform magnetization. So this is the reflectivity, this is the flipping ratio as a function of QZ. And by fitting the data within the GenX program, you can extract both the structural and the magnetic scattering length density. On a slightly more complicated system on the same process, here we've just dusted the iron at an interface. So now what we've got is more of a magnetic quantum well structure. So the induced polarization is confined to this narrow layer. Again, we can simultaneously fit the reflectivity and the asymmetry ratio as you would do in a neutron diffraction, and you measure out what the structural contribution is. And because we're focusing on just the palladium now, this is the induced palladium moment profile as you go across that quantum well. Now, of course, there's iron in the middle, so that's why there's this small dip. There's less palladium here, so the moment is slightly reduced. We can, however, fix the magnetization moments by simultaneously fitting the palladium edge, the iron edge, and PNR, and by simultaneously fitting multiple energies and the neutrons, we are able to get a full description of what the magnetization is doing in that quantum well structure. So you can measure the profile nicely. You can also do element-specific magnetometry. So this is looking at the same reflectivity that we just saw, but you find a Q value somewhere over here where we have a large signal. And instead of looking at the Z dependence, we look at the field dependence, and we can plot out how the iron is behaving and how the palladium is behaving. And we did that as a function of temperature to explore magnetic ordering and critical behavior in these systems. And actually, this is quite a subtle system in that the iron is a two-dimensional XY system, and the palladium is also 2D XY, but because of that susceptibility, you get apparent critical exponents that appear to make the palladium look like it's behaving as a 3D material. Again, we don't need to model the absolute magnitude. This flipping ratio is simply proportional to the magnetic moment. We're not getting an exact value for it. Similarly, we looked at this sort of material structure. So this is samarium, cobalt, and then 2 layers of cobalt, aluminium, zirconium. And what we've done is we've changed the amount of cobalt in these layers. And what happens here is we have a hard samarium cobalt layer, and then we have soft cobalt aluminium layer. And by changing the cobalt contribution, you have different ordering temperatures of the 3 layers. So the question was, how was the profile behaving and how was the magnetization behaving? So if you look at the magnetization, you'll find that the cobalt and the samarium seems to be completely decoupled, which is quite strange, bearing in mind there should be cobalt in this bottom layer. And we argue that's to do with percolation effects, essentially. So you've got this interesting magnetization behavior, which you can track out. There is some exchange bias in this system. So it's very interesting from a magnetic perspective, but we also then modeled the sample across different field steps at the 2 different temperatures. So in the temperature regime where this B layer was magnetic, we fit simultaneously the structure at the cobalt edge plus 3 flipping ratios to plot out the distribution of the cobalt moment. And you can see that at certain fields, this one here, we've started to flip the top layer, and it's introduced a sort of a winding type domain wall into the middle of this B layer. And then at high temperatures, where that middle layer should be non-magnetic, we also see that there's some proximity that's being extended through this layer. But it has seriously come down from here. So by setting up sensible models and doing the simultaneous fitting, we've been able to sort of like probe the magnetic profile as we went through these sort of like tri-layer systems. And in the last minute or so, we've also been looking at the effects of putting dopants in at interfaces to try and understand the Jasinski-Maria interaction and how that couples with proximity induced magnetization. So here we've got a cobalt layer with platinum, and the platinum gets an induced moment at the interface. And then as we start to dust that top interface with either gold or iridium, which have different spin orbit interactions, then we start to measure how that magnetization changes as a function of the thickness of the spacer layer. And then also finally looking at proximity between platinum and ferrimagnets and trying to understand how that induced moment comes about. And from changing the composition of our ferrimagnet from iron cobalt to simply cobalt, it changes the amount of the transition metal. So the spin flop between the iron cobalt and the gadolinium is reversed. And what you measure between whether you put cobalt gadolinium or cobalt iron gadolinium in is that there's a reversal of sign in the induced moment. And essentially what that's telling us is that the platinum induced moment is closely related to DD coupling. It's the DD overlap between the platinum and the iron and the transition metals that's driving that induced moment. And subtly here, you can see that where we have a rougher interface at the top of the sample, at the top of the transition metal layer, we have a higher induced moment and a broader width of induced. So that's a whistle-stop tour of some of the stuff that we've been playing around with, and that these are the conclusions really, that the resonant reflectivity is exploiting anomalous scattering factors. And when we do that, we change the refractive index, we change the contrast of the layers, and that we can get new, potentially more robust structural determinations, but also once we start including some of the magnetization, we get magnetic profiles as well. So that would be normally where I would finish and stop, but because this is the type of meeting it is, I think it's useful to flag up where the issues really stay. So we still have a lot of problems on finding what those optical constants are for real samples, and how transferable an experimentally determined optical constant set for, let's say, palladium on one sample is to another. We have some models about how we can disentangle structural and magnetic interfaces, which may be different, but I think those can still have quite a lot more effort put into. We talk about simultaneously fitting the data, and of course, what you have a problem with is that, of course, the asymmetry ratio is on a linear scale, and of course, the intensity is on a logarithmic scale. So finding the best strategies and the figures of merits and how to proceed is really quite important. And in this example, which is just a simple samarium cobalt layer, one of the things you can see is as you tune to the different energies, so the blue is the lab data. If we tune to the samarium edge or the cobalt edge, the scattering length can go from positive to negative within the X-ray data. And of course, the shape of this interface becomes very complicated in how this is modeled. So if you think of how we normally model an interface between a slab A and a slab B, we put an error function through it, or some such profile. How you profile something which is going in one direction positive and in the other direction negative, and making that self-consistent across the different energies, I think is one of the areas where a lot of this fails and falls down. In terms of X-ray data, the uncertainties in the data itself are not Poissonian, so we don't really know what the uncertainties are, and that does impact how the fit evolves. It takes a long time to do these simultaneous fits, so it's not entirely obvious how you're going to go about and understand where the uncertainties of those SLDs are, because running them things 20 times is computationally very difficult. And we've got to try and move away from this input bias generated by how we set up our models for the fitting. So hopefully that's good. I'm going to stop there and I'll take as many questions as people want to throw at me.